everybody. Welcome back to another episode of the problem solving series. Today's episode, we're going to be going over some specifics for sound waves. So my last two videos have been about periodic motion, aka simple harmonic motion, and mechanical waves. So a lot of the concepts and kind of core things about waves from both of those two videos are also applicable to sound waves, so namely the wave relation, the frequency period relationship, all of those things. I'll kind of pop a summary of the things that are going to be the same over me, so just in case anybody needs a refresher, but if that is not enough, then I highly recommend that you go back and rewatch those, just in case anything I talk about upcoming is a little confusing, or when you're doing your homework problems, if you're still stuck and that's not something I cover here, try and check out those two and see if they give you what you need. So one of the major things that we think about and kind of want to look at when we're talking about sound waves is going to be looking at the intensity. So I guess kind of one of the nicer, maybe not nicer isn't the right word, but I guess more interesting things that we can do with sound waves and that we study a little bit more intently is because sound transfers over to something that we can perceive. It gives us music, it gives us speech, we hear things. Like there's a lot of biological and even psychological connection to sound waves, and kind of pairing those physical signals to the perception that we hear is kind of a really rich area of study for a lot of scientists, and we get into a little bit of that in this course. So when talking about the intensity of a wave is going to be proportional to the amplitude. So a lot of the times we will write that in a way, or an equation in a way that you can compare two different waves and their amplitude. So the intensity of one wave over the intensity of a second wave would be equal to the amplitude of the first divided by the amplitude of the second. So we don't go too much into the constants that give a rise directly to the intensity amplitude relationship, but we do know that there are just constants. So if we do take a ratio, any of those constants would fall out and we're left with that. We can also describe the intensity as the power of whatever sound source we have, if we can assume divided by the area that it has spread over. So intensity really is just power divided by area, and the units are watts divided by meters squared. A lot of the time, especially at this level, of course, we can assume spherical spreading. So if we have a point source, the waves kind of just radiate out in kind of these spherical shells. So the area that we take would be the surface area for a sphere. So the intensity would be the power divided by pi r squared, where r is your distance from the power source. And then lastly, because we are getting into now this connection between what we can perceive and kind of what units of intensity are going to make sense for the human experience versus the actual physical units and the SI units that we've been used to, aka for intensity, these watts per meter squared. We can also write the intensity and convert it in terms of decibels. So because we can hear over such a wide range of intensities, and these numbers can be really big or really small, like to the powers of 10, those don't always make a whole lot of intuitive sense if you're like a sound engineer working with something or someone studying sound. So we come up with this decibel scale to just kind of give a more intuitive sense based on how humans experience sound. So I don't want to harp too much on decibels and like what exactly it means, but I do know that students can sometimes get confused. They definitely get confused with doing the math, because now all of a sudden there's a log that you have to be able to do algebra with, which it might have been a really long time since you've done that. Don't worry about that. We'll cover that in our example problem we do. But sometimes even just the explanation for why we have decibels in the first place, I don't think the why is super duper important, at least not for this. I think it's interesting, but it's not super important. But I will just reiterate that it is kind of drawing this connection between taking those physical units of watts divided by meters squared and putting them in something that humans have a little bit more of an intuitive sense for and make a little bit more sense based on how we interact with sound. And then I'm going to jump into actually the example problem working with those decibels and intensities here. There's two other sound equations, sound math things. I don't know. I don't know what to call this. Topics. That I do want to get to, but they're a little bit disjoint. They don't necessarily go together, so I'm going to separate them each. So let's jump into our intensity problem, and then we'll circle back to those other two topics.
You hear an 80 decibel sound 5 meters from the source. What is the intensity of the sound? What would the intensity at twice the distance be? And if the air temperature is 30 degrees Celsius, how long did the sound take to reach you? Okay, so we have kind of a lot going on, but we'll take it in steps. So at first, we do have this sound level here. Beta is 80 decibels. We have a distance, which I'll call R. And we want to know what I is. So we first don't even really need that R to calculate I because we don't have the power. That's what connects intensity to distance, but we do have the sound level and we have an equation for that. So sound level is 10 log I over I0, where I0 is our reference intensity of 10 to the minus 12 watts per meter squared. We're going to go ahead and I'm going to just substitute in numbers because I think it shows the math a little bit better, and I know that some of you might be very confused on how we're going to deal with that log. So I'm going to go ahead and plug in our 80, and I'll wait to plug in I0 later. That's just a constant. So we're going to start off by dividing that 10, which will leave us with an 8 equals log I over I0. Now this is a log base 10, and thinking way back to your pre-calc log rules, if we have a log of base of something, if we exponentiate this log, so basically we're going to take a base that's the same as the base of the log and put in that exponent log base a, this eliminates the log and pops out and gives us the a by itself. So since this is a log base 10, we want to do that with a 10 here. Typically the way that I write that is I will just do a 10, draw it to the lower left corner of the right and the left hand sides of the equation, and then that tells me you can also then just do like maybe a cross through the 10 and the log to indicate that that's getting canceled out. And then we have a 10 to the 8 equals I over I0. We can go ahead and multiply our I0. Myself. This is also a section that I would say reviewing your exponent rules in general might be nice, because like this is something that you can easily just be like, oh, same bases multiplying each other, the powers add. You don't even have to put it in your calculator, you just add negative 12 and 8 to get 10 to the minus 4 watts per meter squared. Okay, so I'm just going to, now we know that there's going to be a doubling happening, so I'm going to change that to R1, and I1 is 10 to the negative 4 watts per meter squared. And now we want to know what the intensity is if we are at twice the distance. So I'll go down here. So I2 at R2, where R2 is equal to 2 times R1. So this is where a handy little proportionality can come and help. So we do have the equation that intensity is power over 4 pi r squared. But if you're looking at say this is the sound power source. The sound is radiating in rings like this. They should be concentric. So if you're looking at, say, R1 and R2, they have the same, and then I'll just draw some general R, just so you can see that that's how those are related to each other. So if we have the same power source happening, then I1 times R1 squared would be power over 4 pi, and I2 R2 squared, so just multiplying that R squared from the equation above, we can see that since these two things are equal to power over 4 pi, we can also set these two equal to each other. And it gives us this nifty little equation that I will write over here, which is the ratio of I1 to I2 is equal to the ratio of R2 squared over R1 squared. So it's a nice shortcut if you have a cheat sheet and can do that. Because then we have I1, we have R2, and we don't even need to know what those numbers are. So let's just do I1 over I2 is equal to R2 squared over R1 squared. Let's cross multiply since we want that I2 together. So I'm just going to draw that with two arrows like this, so that I1 R1 squared equals I2 R2 squared, and then we'll divide out that R2 squared. So then if we substitute in the fact that R2 is 2 times R1, that quantity squared, we distribute that square, so we get I1 R1 squared over 4 R1 squared. We get the R squareds canceling. And then we can just do 10 to the minus 4 over 4 equals I2, which would be 2.5 times 10 to the minus 5 watts per meter squared. Okay, and is there one more part to this? Oh yeah, what would be, if the air temp is 30 degrees Celsius, how long would the sound take to reach you? So I'm just going to do this. Temperature is 30 degrees Celsius. We're assuming that we're still at that 5-meter distance. So I'm just going to rewrite that here. So we would get the speed of sound, that's the first thing that we want, by using 331 plus 0.6 times the temperature, which gives me 349. And then we would just use our good old distance over time equals v. So we have our v, our distance in this case is r1, and then we could cross multiply t equals r1 over v, which would be 5 over 349, and that time would be 0.014 seconds. So getting to you very quickly.
So another thing that is going to affect the quality of sound and how sound gets perceived is going to be whether or not, if you have a sound source, if that sound source itself has a speed or the observer of that sound has a speed, there's going to be a shift in the frequency that the observer is then going to hear. So this is called Doppler shift, and there's a million different ways that you can write Doppler shift equations. I'm not a fan of a lot of them. I see where a lot of them are coming from, but a lot of them just get really confusing. But before even jumping into that, actually, qualitatively, we have all experienced this, I would guarantee, because when there is a ambulance moving towards us, when it's kind of further away, but then as it gets close and is moving towards us, it sounds so loud and the pitch just gets so high. And then as soon as it passes us and starts going away, now all of a sudden it gets kind of more drug out and the pitch sounds lower. So that pitch is related to frequency. So pitch is a quality that we perceive, but it is related to the physical quantity of frequency. So that's typically what we're talking about when we talk about Doppler shift. It's a frequency shift. I like to write it as F prime equals F times V sound plus V source divided by V sound minus V observer. That is going to take into account that then when you are writing out your velocities, if your source is moving away from your observer, the sign will be negative. If it's moving towards, it'll be positive, and same for the observer. If the observer is moving towards the source, that VO is going to be positive. If it's moving away, that VO is going to be negative. My experience, I've just found that that is the simplest form of the equation that you can get. There's other ways that kind of break it up into conditions of observer stationary, source moving, observer stationary, approaching or retreating, and then those negative signs will change. It'll kind of account for the sign with the plus or minus instead of having to take it into account with the V's themselves. But for these types of problems, I have just found it makes the most sense for myself to have this kind of general form, and then you put the signs in for the V's when you're kind of drawing out your problem and writing out your variables. So let's jump into doing an example so you can see exactly what I'm talking about and see it in action.
Calculate the observed frequency of a 1000 Hz source for the following situations. Source moving at 13 meters per second towards the observer, observer moving at 13 meters per second towards the source, A and B simultaneously, and then negative A and B simultaneously. So this is just to give a nice good feel for Doppler shift and how we want to use the version of the Doppler shift equation that I'm giving you guys, because there's quite a number of ways to write that and kind of deal with this. So first we've got our F is that 1000 Hertz. For A, we're going to focus one at a time, so I'm just going to write the equation then. So we have F prime is F V sound plus V source over V sound minus V observer. And V sound is the speed of sound, which we can assume is 343. So for situation A, the source is moving, but the observer is stationary, so our V observer is 0. And our V source is, so the speed is 13 meters per second. We're going to put a positive on that because it is moving towards the observer. So if it was moving away, it would be a negative sign. And then I guess I'll call this frequency prime A since it's for this first situation. We have the 1000 over 343 plus 13 over 343 minus 0. I forgot a 0 on my 1000. And this is going to give me 1038 when I round it. So this matches with what we expect because we should expect the frequency that we hear to be larger since this is moving towards us. For B, we have the velocity of our source equals 0, and the velocity of our observer is going to be, again, plus 13 meters per second because they're moving towards each other. Our FB prime, 1,000, 343 plus 0 over 343 minus 13, which gives me 1039. So almost exactly the same as above, which we would expect. And then, so what I mean by A and B simultaneously is that the source and observer are moving towards each other with the same velocity. So all I mean by this is V source is plus 13 and V observer is minus 13, which would give us FC prime 1,343 plus 13 over 343 minus 13. Something else you can do, I just usually do this on my calculator because I'm so comfortable with it, but if you're not, you can always do those additions and subtractions first, so you don't have to worry about missing a parenthesis or having your calculator do PEMDAS out of order. So let's see, so this would be 356 over 330, 10 rounded to 79. And then lastly, so what I mean by negative A and B simultaneously is now the observer is still moving, that should be plus. The observer is still going to be moving at plus 13 meters per second. And the source is now going to be moving at negative 13 meters per second. So the source is moving away from the observer, but the observer is moving towards the source. So we'll have F prime D equals 1,000, 343 minus 13 over 343 minus 13. What do you know? We're going to get 330 over 330, so our FD prime would be equal to 1,000, which is what we would expect because they're basically moving, one's moving away and one's moving towards the other, but they're exactly moving at the same velocity, so the amount that it's shifted when it leaves the source will be unshifted when it reaches the observer. Essentially is all what that's saying. So yeah, the only thing I was thinking about changing was if we made it, I don't know, let's just do case E that I'm going to make up, where V source is negative 13 and V observer is negative 13. So we get V, or F prime is F, which I guess I'll keep as 1,000. F prime is 1,000, 343 minus 13, and then this will be 343 minus a minus 13. So that'll become a plus 13. So we get 330 on the top. I'm just going to take this super slow so you can see that negative negative will switch to a positive. We get 330 over 356, which is 927. And in that case, both things are moving away from each other. And so if you're moving away, we would expect our frequency prime to be lower than our original. So that all tracks.
Okay, and the last thing I want to mention in terms of sound waves is just this idea of a beat frequency. So when we have two sound waves of different frequencies interfering with one another, we can get these beat frequencies that come up in between them. So just from the nature of what their frequencies are related to each other, if they're kind of like off by a little bit. Of course, these are the same frequencies. I'll just throw a picture up because I cannot do this with my hands. We basically get, when these two frequencies superimpose, we almost get this envelope wave going over the littler frequency modulations that are happening. And then the frequency of that envelope wave is going to be what we call the beat frequency. The beat frequency is the absolute value of the difference between those two. So you can either see this written as F beat is absolute value of F2 minus F1, or you could see it written as just F2 minus F1, but they indicate that F2 should always be the bigger of the two frequencies when you take that difference. The only thing that can get a little complicated with these is if you are given, say, one of the frequencies that's being subtracted. So let's say that you're given F1, and you're given the beat frequency. Without any additional information, you're not going to be able to say what that F2 is, because technically there's two answers because of that absolute value. So F2 could be 3, let's say if the beat frequency is 3. If the beat frequency is 3 and one of the frequencies is 40, then the second frequency could be 3 plus that 40, so it could be 43, or it could be 3 minus that 40, it would be 37, because if you take the absolute value of the difference between 43 and 40, you get 3, and if you take the absolute value of 37 minus 40, you also get 3. So that's the only thing really to be careful of with beat frequency. I'm not going to even go through an example problem because I just don't really think that it's worth it, to be quite honest. It's, they're not usually that difficult. Just remember to take your absolute value and that there could be more than one answer. Just be careful that if you have, say, a multiple choice with an option that's like cannot compute the second frequency without additional information, that might be the answer that you need to choose come test time. But yeah, otherwise, that's all that I have for sound waves for within the realm of this mechanics course. So I do tutor for a physics of sound course that I will be making some lessons specifically for that go a little bit more in depth, but within the realm of this intro mechanics class, that's all I've got. So until next time, happy physicsing. Bye, guys.
Howitzer, what are you doing? Hey! You gotta say bye to the kiddos. You gonna say bye? You gonna say bye?